Right, here we go. We're starting. Ona actually, this is very exciting. This is like 8:15. We're in astronomy. I have seniors. The class is growing like mold, black mold. Anyway, Ona, what do you got, girl?
Newton's hypothesis.
Newton's hypothesis. We're talking about universal gravitation, and we're talking about Newton's hypothesis relative to his development of universal gravitation. Ona, hit it.
That the moon is actually falling towards Earth.
The moon is actually falling towards Earth. That's correct.
Except the moon has enough
Except what?
the moon has enough tangential velocity to avoid hitting Earth. So it's going fast enough that it's not falling straight towards Earth and drawn by its gravity, but instead it's circulating around.
All right, so say this again. So the moon is orbiting Earth, okay? But it has enough tangential, what'd you say?
Velocity.
Velocity. So what does that mean, tangential velocity? What does that mean? Yes,
I have a good diagram
a diagram.
to show on it. I copied it from the book, but I thought it was very helpful.
Would you like to, let me see it and I'll,
Yeah.
oh yes, thank you. This is actually, thank you, Brianda, nice assist on that. This is astronomy, and the quality of astronomy instruction as to whether or not it's astronomy for poets, astronomy for someone who knows nothing about science, to astronomy for astronomers, depends upon your physics background, quite honestly, physics and math background, because it can get very hairy. It's a capstone course in the sciences, with the exception of biology, but who knows, maybe we will find extraterrestrial life. But let's say that the moon is moving in a linear fashion. Okay. So think of it like this. In other words, think of it like a projectile being thrown horizontally off a cliff, okay? At a certain velocity. It has a certain initial velocity, correct? And so it has a constant velocity, right? So if I throw it off a cliff and there's no gravity there, it's not going to fall. It's going to go a certain distance. And that distance equals VT, correct? Yes? Right? But we know that it's going to curve towards Earth. So let's say in 1 second, let's say that this were 1 second, it would fall here, let's say. Correct? Yes? 1 second, it would fall there. And in reality, that's what? That's going to be the orbit of the moon. In other words, where is it falling? It's falling towards Earth, isn't it? It's falling towards Earth. So you can put Earth in the center of that arc. Okay? So that's where it's actually falling towards Earth. So you can think of it like projectile motion. Look, if I take a rifle, high-powered rifle, and I hold it shoulder height. Okay? Take a high-powered rifle. Okay? And I shoot it, and it's 6 feet off the ground. Okay? 6 feet off the ground. Okay, I'm 6'4", so let's say 6 feet, right? And Brianda's right next to me, and I'll go 1, 2, 3, and I'll pull the trigger, and on 3, she drops a penny. Can you see this on the screen?
Yeah.
This drawing?
Just
Yeah.
don't go any further.
Okay, don't go any further, okay. So she drops a penny, correct? She drops a penny. So right here, is that okay?
Yeah, your arm shows.
She drops the penny, right there.
The very edge kind of shows. But
All right, we'll move it over. We can do this. We have the technology to improve the situation.
the card.
Okay, is that good? Okay. This will go like this, right? That will fall. Now, this is one of the coolest things in introductory physics for students who have never had physics before. Unfortunately, everybody knows what a rifle looks like. People watch the news, AK-47s, M16s, high-powered rifles. It's kind of an unfortunate part of life, but did you know during the Middle Ages, at one point during the Middle Ages, the only product Europe produced that they exported out of Europe was cannons, armament. Isn't that weird? Isn't that horrible? And we haven't changed since. Okay, everything we had in Europe was imported. Well, not everything, but a lot of things were imported, and we only exported one thing. So you want to talk about a trade gap, right? So anyway, when I shoot this rifle and she drops the coin, what's going to hit first? The coin or the bullet? Don't answer him. You had physics. Reem,
Yeah.
what's going to hit first? The coin or the bullet?
Are we dropping the coin or?
We're dropping the coin. She's right behind me. I go 1, 2, 3. She drops it and I shoot the bullet. Boom! And that thing is rocketing, man.
Same.
Brenda.
I think the gun because doesn't it have
The bullet,
more,
you mean?
like- or yeah. No.
It's okay. No, excuse me. She's at least working. Thank you, Amir. Are you even working here, Amir?
Yeah, just answer the question.
Okay, Mr. Bear. Excellent. Yes.
Wouldn't it have more velocity than the penny?
So does the velocity make a difference? Have you ever seen basketball? Do you know what a basketball is?
Yes.
Okay, excellent. Okay, hey, listen, international, you gotta ask, okay?
I'm American.
I know that, I'm teasing you.
Basketball is.
I know that. All right, so you've ever heard of Michael Jordan? They call him Air Jordan, okay? When he runs down the court, he's dribbling, he starts at the top of the key, 2 steps, up, backwards, slam into the basket, right? Now, what's his hang time like, do you think? We're kind of going a little off topic, but there's a point to my madness. What do you think his hang time is? How long is he in the air? 4 seconds, 3 seconds, what do you think? Anybody? 5 seconds?
Depends on like what he's doing.
Yeah.
He's running really fast down the court. He leaps up, backwards, slam, comes down to the floor. What's he do? So you think 3 seconds?
2 or 3 seconds. It won't be much longer unless he keeps on the.
So say 4 seconds, we'll round it, maybe a little off. 4 seconds
2
or
or 3.
3 seconds.
3 seconds? Okay, 3 seconds. Okay, so you're saying, she says 5 seconds, so let's try 5 first and then we'll go to 3, okay? All right, so here's Michael Jordan. Michael Jordan is jumping and coming back down, okay? So right there is 2.5 seconds, right? Because his hang time is 5 seconds, you're saying, correct? Yes? Well, I'll give you, let's say he's right here then, right? So if he's going to fall, I'll give you the equation that can determine the distance that he falls from a 0 velocity, because his vertical velocity right here is 0, right? Correct? His forward velocity is still whatever it is, but the vertical velocity here is 0. If I throw this up before it starts to come down, it has to hit 0 velocity, right? Right? Okay. Well, I'm just going to give you the short form. You don't want me to prove it, right? I'm just going to give you the equation. Is that okay? Okay. So that distance is going to equal, let's bring this down like this. My arm is killing me. So that is going to be 5t squared, right?
Yeah.
So what is, get out your calculators. No, you don't need it. You've worked too hard. Take a break.
Yeah.
Anybody? You got your calculator? Yes. All right, so what is 2.5 squared? What is that?
I can't see it.
33, 34,
31.25.
31. So 31 31.25 meters. So that's about 100 feet. Ish. So do you think that he jumped?
No.
Did he jump? Brianna, you're talking?
I'm pretty
And
sure
not
the
listening?
record's 9.
No, okay. I just want to sound mean on film. But do you get it? In other words, when you do the calculation, Brianda, he jumped, his vertical height was 31.25 meters. Taller than his building, a lot taller.
Oh.
100 feet, okay? Let's try 1.5, because we said 3 as well, so let's try 1.5.
It would be 1.5.
Let's say his hang time was 3,
6.75.
so what is it?
6.75.
6.75, so 1.5 squared times 5 is what?
I did times 3.
No, it's not times 3.
Wait,
It's,
1.5.
it's the hang time, it's the vertical drop, 1.5. If his hang time is 3 this time, excuse me, if his hang time is 3, then the vertical height is at 1.5 seconds, and then he's gonna fall, right? So it would be 5 times 1.5 squared, which is what?
5 times 1.5.
No, 5 times 1.5 squared, remember? It's 5t squared.
11.25.
What is it?
11.25.
11.25. So 11 meters, 33, 38 feet.
But he's not going necessarily like straight, he's going up. It's more of a vertical leap than a horizontal.
You're trying to explain, you're trying to rationalize a wrong answer, which is pretty easy to do,
No,
because it
like-
doesn't matter if you're
I
right.
jump like that.
Yeah,
I'm not really traveling any distance. I'm
Okay.
just jumping
so you
up.
think the vertical, you think the horizontal velocity is going to affect the vertical distance that you jump, or the time in which you stay in the air? That's a good question.
No, like you're gonna travel less distance if you're trying to go higher.
Okay, that's fine. All right, let me ask you this. Okay, so let me just say one more thing. 1.5 is 11. Okay, so that's obviously wrong. But let's just talk about this for a second, because if you don't understand basic laws on Earth, it's difficult to understand them in the heavens. Because if you do, if you don't understand them, you start to think that maybe angels are rotating the stars on crystal spheres. Okay, so it's important to understand this, okay? So what you're saying then is that if I jump up and then jump back down,
Yeah.
all right, and I have versus I jump like this. So I can stay up longer if I have horizontal velocity. A good horizontal velocity, I can stay up longer.
Yeah.
Is that what you're saying?
I'm more talking about the distance. Because like
The distance, what distance? The vertical distance?
we were saying that like if he's up for 1.5 seconds, then he would go 11.25 meters, correct?
Correct.
That no one's ever jumped that long.
That far.
Yeah, that far.
Okay,
But people have jumped for that long.
they have.
Yeah. Like if you see them go up into the air, they're not quite 1.2.
No, what's hang time? Hang time is,
Times in the air, right?
no,
Play
it's-
basketball.
yeah, hang time's in the air,
Yeah.
right? And the height you was, so please stay with me. We're kind of losing people here, but please stay with me because many of you feel the same way. Hang time is the time you're in the air, right? The vertical distance that you achieve would be half of that time. Would you concede that?
Yeah.
Okay, good. So my hang time is longer if I have a horizontal velocity. Is that what you're saying?
I guess.
Okay, all right.
I don't know. I only like I didn't study this or anything like
No,
that.
no, I understand. No, and I'm not suggesting. I know that you didn't study it. That's why you're in here. I'm not making fun of you, and I'm not going to call you terrible names, like whatever. But what I'm trying to get across to you is this, that if Michael Jordan has a hang time of 3 seconds and he only jumps whatever his feet are, what's legitimate in terms of off the ground?
Like a basketball player?
Yeah,
He's about 7 foot.
but no. His feet, how far his feet are off the ground?
0.5 meters maybe?
Half a meter? Okay. So he's going to jump up a half a meter, right? What is holding him up? Vertical or horizontal velocity? What is holding him on Earth?
Gravity. I guess.
Gravity, right. Gravity. And this is what we're trying to get through here. Where does gravity come from?
Many different things.
It comes from the center of the mass, right? Remember we talked about this? All mass has gravity.
Yeah.
Okay, even a small mass, even this has gravity, right?
Yeah.
It's completely and utterly and absolutely negligent, right? So the Earth has gravity, right? So it comes from the middle, right? So it radiates out, right? From the perspective of the surface of the Earth, where is the gravity vector? Where's the ray? Where's the gravity? It's going to be perpendicular to the ground, right?
Yeah.
Okay. So in other words, so it's this. This is the height, and this is also the gravity, right?
Yeah.
Okay. So if gravity keeps the body on the ground, so if I jump, I fall back down because of this vertical force, right? What's the problem? Yes. How could I remain in the air because of a horizontal velocity? Does that make any sense to you? It does. All right. All right, let's skip to the end. Okay. You see, the vertical and the horizontal vectors of projectile motion are independent. Remember we talked the other day about horizontal motion? What keeps that cart in motion? Well, it's in motion itself. It stays that way. And the only force that I have to apply to that cart in the aisle is what? Is to overcome friction, which is a little bit related to gravity in terms of weight and normal and all that type of thing. But it's essentially friction, right? Yeah. It's friction, yes? So if I overcome the friction, the cart stays in motion forever, correct?
Yeah.
Right? Okay. And if I have these two vectors, if I have projectile motion, and I have this, that's the vector, correct? And that vector is going to have a Vx and a Vy. We're not going to solve for that, trust me, we're not going to do the math. But these vectors are independent. This remains constant except for friction. But we're going to pretend there's no friction because in order to work out the initial problems, you pretend there's no friction. But again, this velocity stays constant, right? This is governed by what? This is governed by what? So look at this shape. If this didn't exist, this would just simply keep going, right? But look what happens. It rises because of this vector, it rises, right? Because of this vector, it's moving to the right. You see that? It reaches a certain point here where this vector runs out. It runs out, right? According to gravity. every second it's going to lose 10 meters per second squared, right? It's going to lose 10 meters per second every second based on the acceleration or deceleration of 10 meters per second squared, right? It's going to lose it, negative, right? Okay, or positive depending on your point of view. So then it's going to be 0, then it's going to start accelerating again. So it's going to 50, 40, 30, 20, 10, 0, right? 10, 20, 30, 40, 50, correct?
Yeah.
But this remains constant. This doesn't change. So Michael Jordan only remains in the air according to this vector and no other vector. It doesn't matter if he's running or if he's standing straight and jumping. It doesn't matter. Spud Webb. I think it's Spud Webb, isn't it? I think there's even something in your book. Look at page... chapter 4. Look up chapter 4. Look at page 60. And read about hang time. Okay? Read about hang time. 1.25 meters. That's the, hang time is about 1 second. 1 second. 0.5 seconds here.
Which trap them?
Excuse me?
Which trap them?
Chapter 4 in the book on your thing. Chapter 4, page 60. So look at chapter 4. It's like near the last page in a chapter. It's just an interesting thing called physics of sports. So if you say D equals 5 times 1.5 squared. I'm sorry. 0.5 squared. You'll get D equals 1.5 meters. And that was a little guy who did that, by the way. It wasn't a tall guy. It was a little guy. He had these enormous thighs. He's still alive, I think. What does it say? Does it give the guy's name here? Look up Spud Webb, somebody.
Said he's short.
Yeah, Spud Webb was very short. He was one of the shortest basketball players of his time anyway. Look up Spud Webb.
I think it's 1.25.
1.25. You're right, 1.25. Thank you very much. Thank you.
Spud Webb was 1 meter 70. Weighed 60 kilos.
60 kilos, which is pretty little. I'm like 100 kilos.
Yeah.
I can't even touch the rim. I could barely touch the rim when I was a
No,
teenager.
but 170, that's 14 centimeters shorter than me. That's like,
170 centimeters, is that what you said?
yeah, it's higher.
So divide 170 by 2.54. Divide 170 by 2.54, what do you get?
5 feet.
What do you get in terms of inches? What do you get? What's the number you get? 170 divided by 2.54.
66.92 inches.
So 67? So 67 divided by 12 is 5'7". Right? Who's 5'7" in here? Anybody? You're 5'7"? How tall are you guys?
5'1".
You're 5'1"?
5'3".
5'3"? You're 5'7". Stand up.
I'm 5'7".
What? No, you're not. I am.
I'm
You're taller than me. I'm like
You're not 5'7".
No, she is.
I am.
He's 5'7".
He's not 5'7".
He's not 5'7".
You're not 5'7".
No.
The guy said he's 5'7". So give him a break, will you please? Thank you. Okay. It's not 5'7". Like, was he a liar? Was he going to lie about his height? Give me a break. All right, so the point is this, that when I shoot that gun, that penny, the penny and the bullet will hit the ground at the exact same time. Because horizontal velocity has nothing to do with it. Isn't that weird? It's really weird, isn't it? It's really weird. So when you're talking about the moon falling, if it snaps, let's say the Earth disappears. The Earth just disappeared one day. Gone. The moon, would it continue to go in a circular orbit, spiral out? What would happen to the moon?
It'll go straight.
It would go straight. It would follow that trajectory.
Wherever.
Whatever point, let's say it was at that point right there when the Earth disappeared, it would move tangentially, a straight line that's tangent to that point of the circle. Yes? So, when you say the moon is orbiting, it has that velocity, it has that linear velocity, right? But it's falling towards the Earth. It's the same thing as if you're talking about projectile motion. Same exact thing. What else can we say? Anybody else? What else can we say in chapter 13? Samuel, did you have something to say, or that was just a stretch? You have my permission to stretch. Okay?
Can I have my notes back?
Yes. Yes, very nice. Thank you. So, so in terms of astronomy, it's very important to understand where that circular motion comes from. Where does circular motion generally tend to come from then? Where do you think it comes from? I mean, you can certainly create it like a bob on the end of a string and you're swinging it, circular motion. But where does circular motion in nature come from?
Velocity.
Gravity.
Gravity. Yeah, it comes from gravity.
So gravity likes circles.
Excuse me?
There's gravity, so gravity likes circles.
Everybody likes circles.
Loves it. Creates it. Creates that circular kind of motion. What's the difference between, what's a parabola? What's a parabola? It's parabolic, but what is?
It's like that.
Is that part of a circle? What? That's going to be your assignment for our next. What is a parabola relative to? Is it an ellipse? Is it a circle? Is it? What's a height? What is that? What is that? What is it?
I can draw a diagram for you and give you the equation for a parabola.
Okay, I don't want to. I understand. Basic parabola is y equals x squared. I understand that. But is it part of an ellipse? Is it part of a circle? How does that work? Look up parabola versus ellipse and circle sometime between now and our next class, and we'll discuss it.
But parabolas like continue going.
Yes, but it has that circular nature to it, doesn't it?
Yeah, at the very bottom.
Yeah, that parabola, projectile motion forms a parabola, right? Because you can write the equation for a parabola, similar to projectile motion. So have we finished? The Newton's hypothesis is that the moon is actually falling towards the Earth, but has great enough tangential velocity to avoid hitting the Earth. Okay? So what does that mean, tangential velocity to avoid hitting the Earth? What does that mean?
Like it's going fast enough that those two, like its resulting vector of the Earth pulling on it and then it traveling evens out, so it just.
Yes, this velocity here, if I drew tangents here, they would be fast enough where that would continue
But
to
if it, like,
achieve an
results
orbit.
when it gets out of orbit and it slows down.
Correct. Correct. Okay. Let's talk about, have we finished that? Let's look at the falling Earth. Who's doing the falling Earth? The falling Earth. Anybody? Who's doing the falling Earth? I'm going to get you guys ready for the chapter 13 test, despite your efforts to act like you're dying. Okay? Right? I was an EMT. emergency medical technician, like a paramedic, but not really, sort of. And when someone's dying or dead, they look like this. That's what everybody in here looks like. I feel like I'm in an accident scene, and I know, and you don't realize you have brain trauma. You're just staring at me. Okay. So can we do this? So what does it mean? Who has section 3? The falling earth. They talk about tangential velocity. Who has 3?
That's section, that was in section 2.
Excuse me?
Tangential velocity, that was in section 2.
Yes, but they also talk about it in section 3. There's a nice diagram there. So who had section 3, the falling earth? So you know what? Let's stop this and then we'll start it again, and we're going to keep this 1, 2, 3, etc. Clear? Okay.